Okay, so in this video, we're going to do page 123 in your notes. We are still on section 4.3, but again, on page 123, talking about maximum and minimum values. We're going to take a look at example 1 here, which is this big old function, 3x to the 4th minus 4x cubed. You can see the rest there. Hopefully, again, you're following along in your notes. I'll show you one way people do it. I'm not really too hot on it. I do it a different way, so I'll show you both. You choose what method you like best. But because there's not a lot of room here, I'm going to do it freehand on another piece of paper and then transfer everything back to these notes. So hang on and just kind of see if you can follow this. You are going to get lost at some point, so go back if you need. And I'm trying to make these explanations thorough, but in my experience, that you get better just with practice. So what we're going to do, and what I'm going to try to do here, is we're going to cheat first and take a look at the graph, and eventually we're going to do a function and graph it blind. So I have some values already over here, but we're going to see what the graph looks like just based on what we come up with. But for the meantime, this is what that graph looks like. And you notice it's the highest degree is 4, which means that both ends of the graph will go up. And as it comes down, looks like there might be a minimum there and a horizontal tangent, meaning the slope of the tangent line might be there. What value that is, we don't know yet. And then maybe a horizontal line or a tangent line here with the slope of 0 as well. Looks like there won't be any maximums because these things shoot up to infinity forever. But it does look like that will be a minimum, and not only a local minimum, but an absolute minimum, which we can prove with methods that we've done from previous sections. So let's get started. If I go freehand over here, the best way, and I'm going to try to lead up to something called the first derivative test. And to do that, you got to take the derivative right off the bat. So I think that's 12x cubed minus 12x squared. Notice I'm just using the power rule to solve for this thing, plus 12. So the first derivative test really is a way to see what the slope of the tangent line is doing at any time along your graph. So again, eventually you'll be able to graph this thing blind, but we already kind of cheating, looked at our graph ahead of time. To find the critical values, as in the previous sections, we set this thing equal to 0 and factor it out. Now I'm cheating a little bit because I've kind of gone ahead and factored this out using either polynomial division or a calculator or some kind of computer-aided device. But it factors into that, and I don't know what that is. But if I keep going, this is just the difference of squares. So my 3 factors will be x minus 1, well, x plus 1, this difference of squares right here, and x minus 1. So I really have 3 factors. These two make it kind of a double root. But notice what I've done over on this page. I put the factors here. This is one way to do it. Now, I don't do it this way, but I'll show you this chart method. Some people really like it. It's up to you. What this means over here, though, when you set it equal to 0, is that either x minus 1 has to equal 0, which means x is going to have to equal 1, or x plus 1 will have to equal 0, or x will equal negative 1. So these are the two values that are my critical values, my critical points, when my slope of the tangent line is 0. So already, again, because I'm cheating, that's going to be at negative 1. That will be at positive 1. So what's happening, what I'm doing is I'm chopping up my graph initially, and you look over here, those are my low and that high. So those are the 2 times, just like, again, from over here. So that's at 1, so the tangent line will be 1, and this will be negative 1. Now, I'm going to cheat and draw the graph right off the bat, but look at what's happening between this horizontal tangent and this one. As you go here, my slope of the tangent is always positive. Before it, here's where it also is 0. The slope of my tangent line is always going to be negative. It's getting less negative and then to 0. But before negative 1, it's always negative. Between, between -1 and 1, my slope in here will always be positive. And then once I hit this slope is 0 here, things will turn positive as far as the slope goes. And so you'll see that if I kind of mimic that in here, I don't know how good of a job I'm going to be able to do as I create this thing. And I'm really cheating, but hopefully you get the gist. What's going on, and so those are the first two values that I always try to graph or come up with. Those critical points will tell you something's going on in between here, after here, or before here. In other words, between before, in the middle, and after, because I only have two things where the slope is equal to 0. Notice my slope will be 0 here. Slope of the tangent line will be 0 here as well. So what I do is I always just graph these 2 points right off the bat, and then I check in between, before and after all of them. Even if there's a bunch of points, I check in between and after all of them and see what the slope is doing. That's what this method does at the same time. So in other words, over here, visually, my slope is negative, right? So this thing is going to be said to be decreasing. I can cheat. I already know the answer. X is going to be less than 1 here. Well, for all values less than 1, I should say. I can say this is decreasing. But I'll show you why. My derivative here is negative everywhere. If I took the value, if I took -2 and plugged it into my derivative, remember this is your derivative, for all the values before -1, -3, -2, -1.5, the slope would be negative. So this is going to end up being negative. And nobody does it backwards like this, but usually what people will do to get these answers will be to come up here to the derivative and plug in values. For instance, a value less than -1. Let's do -2, for instance. If I plug -2 into the derivative, and I plug -2 here, -2 plus 1 would give me, -1. -2 here minus 1 would give me -3. And -2 here would give me the same value, -3. And if I computed all those together, a negative times a negative times a negative is going to be a negative. And I don't really care about the fact that this is going to be a -9. I just care about this sign, meaning that my slope everywhere here, the slope of the tangent line will be negative. Could be this way, could be this way. But in this case, it's doing this. Everything's negative. So what will happen is, if I plugged it again, -2 into here, this was a negative, this was a negative, and this was a negative. So what people do chart-wise, they will plug in what happens just to each factor to determine if the slope is going to be negative. So they'll say a negative times a negative times a negative. Well, negative is positive, positive times a negative is a negative. I don't ever do it that way. I just always test a point here less than -1, less than my critical value. And if it's true for one value, it'll be true for all of them. So that's my version of the first derivative test, which is coming up here formally in a second. If I did this chart again for values between -1 and 1, you could do the same thing. So 0 lies in there, and we can visually, again, we're cheating. We're looking at the graph first, but the whole goal is to be able to either use the table or do what I'm trying to suggest to you in the first place. So notice if I took 0, the slope in between here, again, I'm giving you the answer, is positive, more positive, more positive, less positive, less positive. I'm just talking about how the slope is changing. But everywhere the slope's positive. So this is going to be positive, and this is going to be increasing. But again, if I didn't know that and I covered this up, if I were to plug a value in between -1 and 1, 0 for instance, if I plugged in 0, my f at 0 would be, 0 plus 1, I'd have a positive 1. 0 minus 1, I'd have a -1. And 0 minus 1, I'd have a -1 again. So what happens, positive times a negative. And notice I'm going to carry those signs into these factors here. You can do this if you needed to. The first one ended up being when I plugged in 0 positive, and then negative, and then negative. So what happens to your derivative, or the slope, everywhere between there is positive times a negative is a negative, times a negative becomes positive. So which is why we're calling it increasing. So if you like this table method, and maybe we'll do this one next first, we can determine what's going to happen after 1, or that other critical point, plugging in 2, for instance. If I plugged in 2, that's anywhere after 1. 2 plus 1 is going to give me 3, and that's a positive 3. So 2 plus 1 would be 3. Next value, 2 minus 1, that would be a positive 1. And because I have another one of the same thing, a positive 1. So what ends up happening, even remember up here, that ended up being positive, negative, and negative, which was a positive 1. Over here, you're going to end up with a positive and a positive and a positive, which ends up being a positive. So your derivative after 1, for all values of x after 1, will be positive, which means it's increasing by definition. So again, I'll carry these signs over, positive, positive, positive. And that's what some people like to do to create this, because then you'll know for values less than -1, this is decreasing. Your slope will always be negative. For values in between -1 and 1, it will be increasing. And for values after 1, it will be increasing as well. Now, what I like to do is I just test a point. I do the same thing, but I don't write the chart. I will write these lines physically, and they're not asymptotes. They're not really on the line. But what I'll do is I'll take any point in here, and we already did it, -2. So I'll put the derivative over here at -2 is less than 0. That just means it's negative. This is how I do it. In between here, remember we did 0. I'll plug in a point. I'll test a point the same way this chart does. But when I test a point, if it's positive, over here, I'll just say f at 0 is bigger than 0, which means it's positive. I don't go through and do all this stuff. I kind of just plug in a point. And then after 1, remember we plugged in 2. So I'll say f of 2 is greater than 0, so it's positive. Now what that does for me is I look only at these values. So if I know my graph goes from a negative to a positive, remember the last problem, we said that anything that goes from negative to positive slope after a critical point, so up to a critical point, negative to positive, then you're going to have, by definition, a local min. So that's how you prove it. And down here in the formal definition, that's exactly what's going on. If you change from from a negative, check out right here for the first part, for part B, if you change from a negative, the derivative goes from negative to positive at this value, then there's a local minimum. So what you can do, local minimum. So at x equals -1, I don't know if you can read that or not. Now, if the converse was true, and let's just pretend this isn't my graph, but again, we did this on the last problem. If this was your critical point, because the slope of the tangent line here is 0, if you went from positive slope to negative slope, that's called using the first derivative test to determine that you have a maximum. That would be A here. So if the derivative goes from positive to negative, then you have a max. If, lastly, it doesn't change, now notice over here, there's a critical point that says you might have a max or minimum, but the slope before 1 is positive. It's going from here, it's going positive, positive, less positive, less positive, and it hits 0, but then it starts on positive again. So if there's not a sign change, then it's not a max or a min, and you don't, well, that pretty much rules those 2 options out, okay? That's something called an inflection point where you change concavity. But in the future, we'll talk about concavity, where this will be concave up. Anywhere that your graph looks like this, and something like this will be concave down. So notice this will be concave up. Telling you a little bit for the future to here. It's called an inflection point, and then you go, and I don't really know if it's here or not. concave down, concave up. And that's when we start looking at second derivatives. There's also another test to employ for that. But hopefully that helps. This is also an absolute minimum because this is the lowest value. And this function as well, just like the last graph, does not have a absolute max or even a local one for that matter. Hope that helps. It's confusing, but that's why I wanted to walk you through this live as I was doing it. And next video we'll practice some more, and I'll throw another rule at you. Okay.